Today we will consider eigenvalues and eigenvectors and also linear independence. We'll start with eigenvalues and eigenvectors. So let's let A be an n by n matrix. Okay, so then the map X goes to AX for X, a vector in Rn. So for X is going to be an n by 1 column vector. Column vector. So this defines a function from Rn to Rn. Rn to Rn. And such functions are called linear transformations. And they're studied in linear algebra. Okay, so each matrix, n by n matrix, defines a linear transformation. Other matrices, whether they're square or not, define linear transformations also, but we're interested in the case when A is square. Okay, so to understand this linear transformation, it's interesting to consider vectors which are transformed to multiples of themselves. Vectors which are transformed to multiples of themselves. So what does this mean? This means we're looking for a vector x which gets sent to a multiple of itself, say lambda times x. So this is what AX is. So we're looking for vectors. So we want AX to be some multiple lambda of x. For lambda, some scalar. Lambda is a scalar. Okay. It means a real or complex number, of course. So, in such a situation, we make the following definition. We call a vector V, which is non-zero. So notice that if you put x equals 0, it certainly A times 0 is 0. So 0 is always sent to itself. So it's only interesting if it's non-zero. We call it an eigenvector if it satisfies the above equation. Eigenvector for A if A times V is equal to lambda times V for some number lambda. Okay, and in this case, the number lambda is called an eigenvalue. An eigenvalue associated to the eigenvector V. or rather, I should say the. So to each eigenvector, there is a unique eigenvalue. This is the corresponding lambda. It's the eigenvalue associated to the eigenvector v. The eigenvector v. Okay. Okay, and so how do we find eigenvalues and eigenvectors? So basically, we want to solve this equation. This is the eigenvalue, eigenvector equation. Notice this corresponds to ax, this is equals lambda x. This is n equations. This is the matrix form of n equations. This is a non-homogeneous equation. You can think of this as. And the unknowns here are x and lambda. So x consists of n. This is an n by 1 vector. So there's n unknowns there, and lambda is 1. So you have n plus 1 unknowns, n equations. And in general, I mean, that typically will not have solutions, or, I mean, it's not so easy to see what the solutions are. It's overdetermined. So how do we find eigenvalues and eigenvectors? Okay, so notice that, so notice that the equation so instead of x, we will call it v. Let's say AV equals lambda v can be written A minus lambda I v equals the 0 vector. Okay, so how does this help? So if you call this part here, let's call this B. So B again is an n by n matrix. Okay, it depends on lambda, but it's still an n by n matrix. So B is n by n matrix, which depends on lambda, of course. And when you multiply this by V, you get the 0 vector. So V, we want it to be non-zero. So this means that so this corresponds to a homogeneous system of equations, and it has a non-trivial solution. Okay, and this is only possible if B is not invertible. So this equation has a non-trivial solution. Solution V. You can think of this as a system of equations if and only if B is not invertible. And we know that invertibility is determined by the determinant I, if and only if the determinant of B is equal to 0. Okay, so this is the equation that we're interested in. So the determinant of this, it turns out that if A is an n by n matrix, the determinant of A minus lambda I equals 0 gives us a degree n polynomial. And the roots of that polynomial will give us eigenvalues. And for each eigenvalue, we can find at least one eigenvector associated to it. So let's see how it works. So example, let's say 1. So let's find the eigenvalues and eigenvectors of the matrix. A is equal to 1 minus 2, 3 minus 4. Okay. So we write down our eigenvalue equation. This is the so-called characteristic equation. So determinant of A minus lambda I, this is 1 minus lambda minus 2, 3 minus 4. And you'll recall we put these vertical lines to denote determinant. Okay, and we can compute that this is 1 minus lambda times minus 4 minus 3 times minus 2. Okay, so this is a sorry, there's a slight mistake here. So there should be minus 4 minus lambda, of course, here. Okay. So let's correct this as well. Okay, so this is a quadratic equation, and this is lambda squared, and we have plus 4 lambda minus lambda's minus 3 lambda, plus 3 lambda, and you get plus 2. Okay, so the characteristic equation is that we want this to be 0. And you can easily factorize this. This is lambda plus 2, lambda plus 1 equals 0. Okay, so this is as we said. So the equation determinant A minus lambda I equals 0, this gives us degree 2 polynomial. So this is a quadratic equation in lambda, and the roots of that, it has 2 roots. They may be distinct, repeated, or complex. In any case, there's always 2, and each root is an eigenvalue. Okay, so the eigenvalues of A are lambda 1 is equal to minus 2 and lambda 2 is equal to minus 1. Okay, so we have 2 eigenvalues, and for each eigenvalue there is at least one eigenvector. So we do this in turn. So let's first look at lambda 1. And to find eigenvectors, we have to solve A minus lambda, so here's going to be lambda 1i times v equals 0. So this gives eigenvectors. Okay, associate corresponding to the eigenvalue lambda 1. So when you put lambda 1 equals 2, we get here, this is going to be the equation 3 minus 2 3 minus 2 times v1 v2 equals 0 0. Okay, so this is this equation, and now we solve this. So we've been solving these for some time now. So we solve this by Gaussian elimination. So how does this work? So you write down the augmented matrix, so 3 minus 2. So actually this is rather simple. We could probably do it with that. We can do it easily without Gaussian elimination, but let's try it with Gaussian Gaussian elimination. So if we subtract the first equation from the second equation, you get an identically 0 equation here. And you can divide the first row by 3. 1 minus 2 over 3, 0, 0. Okay, so we have a free variable here. You can see here are the there's a leading one here, and there's no leading one in the second column. So there's no leading one here, so no leading one here in the second column. So we have x2 is a free variable, or v2 if you like. So v2 is a free variable. And you can see all the solutions of this. So the first equation is v1 minus 2 over 3 v2 is equal to 0. v2 was a free variable, so you see that you get the set of all eigenvectors. So v is equal to 2 over 3 v2 and v2, where v2 has to be non-zero, otherwise you get 0, 0. This gives us all eigenvectors. All eigenvectors associated to our eigenvalue. So lambda 1 is equal to minus 2. Okay, and now you repeat the same idea for the other second eigenvalue. So this was minus 1, and here we're looking at 2 minus 2, 3 minus 3 times v1 v2 equals 0, 0. Okay, and if you solve this, you get it's easy to check that this is, you get v is equal to, it's going to be in this case v2 with v2 non-zero gives all eigenvectors. Corresponding to the second eigenvalue. Okay, so that's a simple case, and we can do this in arbitrary dimensions. So here's an example of a 3 by 3 matrix. Let's find the eigenvalues and eigenvectors of the matrix. So here's a 3 by 3 matrix. Okay, so this is 0 here. Okay, so 1, 1, 2, 0, 2, 2, minus 1, 1, 3. So it's a 3 by 3 matrix, and the exact same, we apply the exact same procedure. Okay, so we solve first, to work out the eigenvalues, we should solve the equation determinant of A minus lambda I is equal to 0. So this is 1 minus lambda 1, 2, 0, 2 minus lambda 2, minus 1, 1, 3, minus lambda. So we want this is equal to 0. Okay, so this is the eigenvalue equation. The definition of the determinant, recall, it was cofactor expansion along the first row. You can do it along the second row, so it's got 2 non-zero entries, but let's do it along the first. That was the definition. So it's going to be 1 minus lambda times the determinant of, delete the first row and the first column, So you get 2 minus lambda, 2, 1, 3 minus lambda. And then you subtract 1. This is the next second entry in the first row. And now delete the first row and the second column. You get 0, 2 minus lambda, minus 1, 1. And we have to add it to 2 times. That's the last entry in the first row, with delete the first row and the last column. 0, 2 minus lambda, minus 1, 1. So I think I made a mistake here, and let's just correct this. So here we're supposed to delete this, and then you can see that you have 0 minus 1 and 2, 3 minus lambda. Okay, and when you multiply this all out, you get a cubic equation in lambda. You can see that the first equation here, the 2 by 2 determinant is going to be a quadratic equation in lambda, and you multiply by 1 minus lambda, you get a cubic equation in lambda. So you want this all to be 0. So let me not do the computation. I'll just write down the finance, and then you have a cubic equation. You want to factorize it, and you can factorize it. So I'll leave it for you to check. You get lambda 1 minus lambda, lambda minus 2, and lambda minus 3 is equal to 0. Okay, it's a cubic equation. You get 3 solutions, so they're all distinct here. So we get lambda 1 is equal to 1, lambda 2 equals 2, and lambda 3 is equal to 3 are the eigenvalues. Okay, so we have 3 distinct eigenvalues. For each eigenvalue, we have at least one eigenvector, and we proceed precisely as before. So you pick each of these in turn. So let's do it for the first one. Lambda 1 equals 1, and we want to solve the equation A minus lambda 1I is equal times V is equal to 0. So lambda 1 is just 1. This is A minus I times V is equal to 0. Put a line under 0, so vector 0. So this is it's a homogeneous linear system, 3 by 3 linear system. We want to work out the set of solutions of that. So let's write down the augmented equation of this. This is 0, 1, 2, 0, 1, 2, minus 1, 1, 2, 0, 0, 0. Okay, we want to solve this system of equations. So this is the augmented equation of it. And we look in the first column, it's non-zero, and we want to get a 1 as the first entry. So here, if we switch the first and third rows, okay, I'll write it here. I mean, sometimes I don't bother writing what the corresponding row operations are, but you can easily work them out. So here, we switch the first and third rows, and then we want to multiply by minus 1 also. So and you leave the other middle row as it is. And we proceed like this. Then you multiply row 1 by minus 1. So you get 1, minus 1, minus 2. And now, okay, so the first we have a leading one in the first row. Below that are all zeros, and you have a leading one also in the second row, so that's also good in the 2-2 entry, and below that is a non-zero entry. So if you add the second row, or rather let's multiply by -1 the second row and add it to the third row. We get 1 minus 1 minus 2, 0, 1, 2, 0, 0, 0. And this is now in row echelon form, and you can go one step further here. So here we can see, we can solve the equations here. It's a little bit easier if you go one step further. So if you now add the second row to the first row, so let's do it like that. So here you have, so we have leading ones here, and you see that the last row has no leading one. So there's no leading one here. So you get V3 as a free variable. Okay, whenever we look for eigenvectors, we will always have a free variable, because we know our original matrix is not invertible, so there has to be a free variable. And you can easily check that V is equal to, in this case, you get 0 minus 2v3, v3. So this gives us all eigenvectors. So V3 had better be non-zero, otherwise this is not an eigenvector. And gives all eigenvectors. Associated to our eigenvalue lambda 1 equals 1. And we can argue similarly for the others. So let me just tell you the answers. So for lambda 2 is equal to 2, we do the same thing, and you get V equals V2, V2, 0. Gives the eigenvectors. So here V2 has to be non-zero, of course. And for lambda 3, we get, so in this case, 2v3, 2v3, v3. So v3 non-zero. This gives the eigenvectors, gives all eigenvectors. So I should say here maybe all. Okay. Okay, so that's 3 by 3. I said that the eigenvalues may be real or complex. So let's look at a case where we have complex eigenvalues, and we'll see that if the matrix is real, then the eigenvectors must necessarily also be complex. So, so this is example 3. So let's find all eigenvalues and eigenvectors of the matrix A. So this is a 2 by 2 matrix. 1 minus 3, 5 minus 3. Okay, so again we write down the equation, the characteristic equation. This gives us the eigenvalues. So we want the determinant of this to be 0. So this is 1 minus lambda minus 3, 5 and minus 3 minus lambda, and we set this to 0. This is 1 minus lambda minus 3 minus lambda, and it's plus 15 equals 0. It's a quadratic equation of the form lambda squared plus 2 lambda plus 12 equals 0. And this has no real roots, so we complete the square to see what the complex roots are. You can write this as lambda plus 1 squared is equal to minus 11. Okay, and from that you see that lambda 1 is equal to minus 1 plus I times square root 11. So here I denotes the square root of minus 1, of course. And lambda 2 is equal to minus 1 minus I square root 11. So here I is square root of minus 1. Okay, so we have two complex eigenvalues in this case, and they are conjugate to each other. It's as we expect. So this is a quadratic equation, a real quadratic equation. It either has real distinct roots, a real repeated root, or a pair of complex conjugate roots. So when you have real equations, the complex roots will always occur in complex conjugate pairs. And moreover, so let's notice let me mention the general case. In fact, the eigenvectors will also occur in conjugate pairs. So notice that. Let's consider the general case. Suppose that V is an eigenvector. For lambda, for rather a matrix A, which is a real matrix. For a real matrix A corresponding to an eigenvalue to a complex eigenvalue lambda. So we have A minus A V is equal to lambda V. So then, if we take complex conjugate of both sides, we get A V bar is equal to lambda V bar. So bar here means conjugate. So the right-hand side, when you take the conjugate of a scalar multiple of V, this is lambda bar and V bar, of course. And A, since here when you take the conjugate of A V, this is A conjugate, but A is real, so it's itself, times V conjugate. So what do we have? We have A V bar is equal to lambda bar V bar. Okay, so we see that if V is an eigenvector of A corresponding to an eigenvalue lambda, then V bar, the conjugate of V, is an eigenvector associated to the eigenvalue lambda bar. So we have V bar is an eigenvector associated to the eigenvalue lambda bar. Okay, so this is a general fact. I mean, so in our case, if you find eigenvalues associated to lambda 1. So here in our case, we have lambda 1 is minus 1 plus I root 11, and lambda 2 is equal to lambda 1 bar. So if we find eigenvectors associated to lambda 1, then their conjugates will be eigenvectors associated to lambda 2. So it is sufficient just to find eigenvectors associated to lambda 1. To find all eigenvectors associated to lambda 1, since their conjugates will be eigenvectors associated to lambda 2. Okay, so how do you find eigenvectors associated to lambda 1? So lambda 1 is this, and you proceed exactly as before. So you write down a minus lambda 1I times v is equal to 0. So this is a homogeneous system of equations, and we write down its augmented matrix, and you get 2 minus I root 11 minus 3, 5 minus 2 minus I root 11. Okay, so this is the augmented matrix of our homogeneous equation, and we try to transform the 2 by 2 matrix to the left here into row echelon form. So you proceed exactly as before. So if we divide the first row by 1 over 2 minus I root 11, we'll get something like this. So this is 1 minus 2 over 5 minus I root 11 over 5, and 5 minus 2 minus I root 11. Okay, you can check this. Okay, so we have a leading one in the first row, and then you multiply the first row by minus 5 and add it to the second row, and that will be a new second row. Okay, so the first row remains as it is, minus 2 over 5 minus I root 11 over 5, and the second row will become 0, 0. Okay, so we expect to get a row of 0. So this matrix is not invertible. We know that its determinant is equal to 0, so it's not invertible. Eventually you must get at least one row of zeros. So we get this. Okay, and from that you have a free variable. So we have a leading one here, and you have a free variable here. So this is free variable. So you get v2 is free variable. And you can see that v is equal to 2 over 5 plus I root 11 over 5 times v2 and v2. So this gives us all eigenvectors. So here v2. So here v2 is allowed to be any non-zero complex number. In fact, we can take this to be any complex number. So this gives all eigenvectors associated to lambda 1. Which was minus 1 plus I root 11. And you can see that each eigenvector, whatever v2 is necessarily complex. There can be no real eigenvectors associated to this eigenvalue lambda 1, simply because we know that the conjugate of that eigenvector must be an eigenvector associated to lambda 2, and an eigenvector, if it was real, its conjugate would be the same, and so this would mean that eigenvector would be, that vector would be an eigenvector for both lambda 1 and lambda 1 bar, which is impossible clearly. Okay, anyway, so that's how it works in the case when you have complex eigenvalues and eigenvectors. Okay, so that's enough for eigenvalues and eigenvectors. Now let's consider linear independence. Okay, so given vectors v1, v2 up to vn, so these vectors, I mean, so we can think of these as just in general, we should think of these living inside some abstract vector space, but for us, I mean, for example, we can think of elements of Rn or C, or I mean Rm or Cm or something like that. But then, so vectors are things you can add and multiply by scalars, and that's the general definition of them, really. Anyway, so if we're given vectors v1 up to vn, a vector of the form so if you multiply v1 by a scalar c1 and v2 by c2 and add them all together, so vn by cn, so where c1, c2 to C, and these are constants. So these are scalars. So scalars means if these vectors we're thinking of, so for us we'll typically think of complex vectors. So these are complex numbers. So we say that the numbers, we call them scalars to distinguish them from vectors. So any vector v written in this form, we call it a linear combination. Of the vectors v1 to vn. And so that's the definition of a linear combination, and now we can define what linear independence is. So we say that v1 up to vn so vectors v1 up to vn are linearly independent if whenever this linear combination equals the zero vector, then C1 up to Cn are 0. Okay, so basically this linear combination is 0 implies that the constants C1 up to Cn are 0. So certainly if you put C1 up to Cn equals 0, the linear combination on the left is obviously the 0 vector. We're saying if the converse holds, if each linear the linear combination is equal to 0 precisely when C1 up to Cn equals 0, then we say that the vectors are linearly independent, and if they're not linearly independent, we call them linearly dependent. Otherwise, we say that the vectors v1 up to vn are linearly dependent. Or linearly dependent. Okay, so note that below. Okay, so let's note that if v1 up to vn are linearly dependent, so then there are constants, or rather scalars, then there are scalars or numbers c1 up to cn, such not, and the key point is not all zero, such that C1 V1 plus C2 V2 is equal to the 0 vector. Okay, so obviously if I put all the C's, Ci's, C1 up to Cn are all 0, this is obviously 0. So we have that these vectors are linearly dependent precisely when we can find constants or scalars C1 up to Cn not all 0, such that the linear combination C1 V1 plus C2 V2 up to Cn Vn is equal to 0. Okay, so now suppose that suppose that the above equation holds. Suppose that C1 V1 equals 0 holds with C1 up to Cn not all 0. So if and suppose that Ci is non-zero, so then Vi is equal to minus C1 over Ci V1 minus up to Ci minus 1 over Ci Vi minus 1 minus Ci plus 1 over Ci Vi plus 1 minus all the way up to Cn over Ci Vn. Okay, so basically what we take is we take the term Ci Vi to the right hand side, or we take it to one side, and then divide by Ci, and you get this, right? So we can see that Vi is a linear combination of the other vectors. So Vi is a linear combination of the other vectors. And so we see that vectors v1 up to vn are linearly independent precisely when no vi can be expressed as a linear combination of the other vectors, of the remaining vectors. So it's somehow saying that if you're interested in the set of all linear combinations of the vectors v1 up to vn, if you remove one of the vi's, then the set of linear combinations gets smaller. So if you're interested in the set of all linear combinations of these, you need all of the vectors here. None of them are unnecessary in a sense. Okay, so we'll see how that works. So typically we're interested in a subspace of a certain vector space, and we want to find a minimal set of vectors whose linear combinations will generate it. And linearly independent will give us that minimality there. So if you remove one of these, then the set of vectors generated by them will get smaller. Okay, so let's look at a few examples. So example, let's say, is the set of vectors maybe I should write these out. Is a set of vectors. Let me write them out in full for you. Is a set of vectors, let's say v1 equals 1, 3, 6, comma v2 is 3, 4, 5, and v3 is 5, 0, minus 9. So is this set of vectors linearly independent? Okay, so how do we check? So suppose there's some linear combination c1 v1 plus c2 v2 plus c3 v3 is the zero vector. So if necessarily c1, c2, c3 are all zero, then the vectors will be linearly independent. If you can find c1, c2, c3 not all zero, such that the linear combination is zero, then the vectors are linearly dependent. Okay. So this is a linear system that we need to solve. So let's write down this linear system. So this linear system is C1 plus 3C2 plus 5C3 equals 0. 3C1 plus 4C2 equals 0, and 6C1 plus 5C2 minus 9C3 equals 0. Okay, so so this vector equation corresponds to these three equations. This is a homogeneous 3 by 3 system of equations, and we know how to do these by now, so we can look for all solutions of this. So we write down the augmented matrix. 1, 3, 5, 3, 4, 0, 6, 5, minus 9. So this is the augmented matrix. And we do row operations on this. Okay, so I won't write down what they explicitly are, but when you do row operations on this, you get the corresponding. We can transform it to this. So exercise, do this. And here, the matrix, now it's on the matrix here is row reduced. So this is, row echelon matrix. This is a row echelon matrix. And from this, you can see that you have a free variable. So V3 is free variable. And you get, so you have V3 is a free variable, and that's all we need to know. So we have a free variable. So it means there exist non-trivial solutions. I should call it C3. So C3 is a free variable. So there are non-trivial solutions. And what does that mean? We have non-trivial solutions, so we can have solutions where not all C1, C2, and C3 are 0 in this equation. So we can find a solution with C3, C1, C2, C3 not identically 0. So this means that V1, V2, V3 are linearly dependent. Comma V3 are linearly dependent. Okay. So we can also consider linear independence and linear dependence for functions. So definition, we say that a set of functions f1 up to fnt is linearly. Okay, previously I just said vectors v1 up to vn. I couldn't say here the functions f1 up to fn rather than a set. Anyway, I've written this. It doesn't really matter. I mean, so here we're saying that this set is linearly independent. On an open interval I if the equation C1 F1t plus up to Cn Fnt is equal to 0 for all t in I implies that C1 is equal to C2 is equal to Cn is equal to 0. And similarly, the functions are, otherwise we call the functions linearly dependent. Dependent. Okay, so yeah, let me stop here. So next time I will give you examples of linearly independent functions, and then we'll move on to the basic theory of first order linear ODEs.